Welcome back. In today's lecture, I am going to talk about the non-linear space. Okay, I am going to see that how basically notion of non-linear space comes into picture and why this non-linear space is very much important for us. Okay, so before going to the notion of non-linear space, first I am going to revise the previous lecture because notion of norm are very much connected with the notion of inner product. Okay, and we have already seen that whenever there exists a inner product of two vectors, and if I take the square root, then norm comes into picture. Okay, so it looks like that norm and inner product are actually connected with each other. Okay, but it is possible to show that if I have inner product of two vectors, okay, then there always exists norm. But in reverse way, it might possible I can define a norm, but there is not any inner product. Okay, and due to that reason, in today's lecture, I am going to give the separate definition of the norm of some vector. Okay, so and why that notion is required, because whenever we are able to define the norm, we are able to talk about the length of some vector. Okay, in generalized space I can talk about the length. Okay, and later using that concept I can able to see the distance between two vectors also. Okay, so I can talk about the nearness of two vectors. Okay, and due to that reason this concept is very much important to talk about the convergence in some space or something like that, or in more broader sense, suppose that I want to talk about limit in higher dimensional space. At that time I have to involve the notion of norm. Okay, particularly whenever we are in the vector space. Okay, so let us again recall the previous class. So what we have seen in previous class, that whenever we are talking about Euclidean space, so whenever I am talking about Euclidean space, it means that I am going to talk about those kind of space where the field element is real. Okay, and after that I have generated vector space over this real number, and another thing is that we are going to define the distance using some kind of norm. Okay, so and if you see the Euclidean space, then I know that how to define the length, how to define the angle. Okay, and during from school time onward we are seeing this, that suppose I have some point here, and we know that if this is x-axis, this is y-axis, this is z-axis, then what is length of this vector? We are actually well aware about this fact that is x square plus z square, like that. So in this way we are defining the distance. Okay, whenever we have vectors, we are also able to understand that what is angle of this vector with respect to x-axis, y-axis, z-axis. Okay, so we have two different familiar concepts. And now if you do abstraction, okay, so notion of length I have in this Euclidean space. Now I am going to generalize it. Okay, so generalization of this is nothing but the abstract notion of norm. Okay, similarly whenever we are talking about the angle between two vectors, at that time we are taking the help of dot product. Okay, you might be aware that v dot w equal to magnitude of v, magnitude of w, and cos theta. Okay, so using this dot product I can able to talk about the angle. Okay, and if you do the abstraction of that, then notion of inner product comes into picture. Okay, so how basically mathematics are evolved, they are seeing something in in the Euclidean space where field element is real, we are just talking about real. Now we are going to talk about general space. General space means where functions are involved, matrices are involved, polynomials are involved, or we are also open the door if some new technology comes into picture such that I can able to incorporate and I can develop some kind of language such that using the help of mathematics we can capture this. Okay, and in previous class we have already talked about this, the notion of the inner product, how basically notion of inner product comes into picture, what is meaning of inner product space. So whenever we are talking about inner product space, then we are talking about some kind of vector space, and that vector space is occupied with the inner product. And I have already told you that whenever inner product comes into picture, then I can able to define some notion of NOR. Okay, so inner product space is nothing but vector space together with inner product. Okay, and with help of that inner product I can define the NOR. Okay, so in this way we are telling that vector space is there are some difference between vector space and inner product space. Okay, in vector space there is no notion of length and angle. Okay, but whenever we are talking about inner product space, then I have some notion of the angle and notion of the distance or length. Okay, so notion of length is given by the NOR, notion of the angle that is given by the inner product. Okay, so now if you see these two space, then there exist two different inequality. And if you see the literature, whenever we are doing the manipulation, at that time we are using these two inequality, that is called Cauchy-Schwarz inequality and triangular inequality. I hope that most of you already come across these two inequality. Okay, but you have to understand this inequality is basically valid in any kind of inner product space. Okay, it means that if I have some kind of inner product space, means vector space together with the inner product, and I obviously whenever I am talking about inner product means there some axioms should satisfy, some definition should satisfy. Okay, we will again revise it. Okay, so if you see the Cauchy-Schwarz inequality, so that is nothing but the inspired from the geometrical interpretation of the dot product. Okay, and similarly if you see the triangle inequality, that is the length of any side of triangle is the bounded by the sum of the length of two sides. So somehow you can tell that this is inspired from the length. Okay, and triangular inequality is obvious consequence of the Cauchy-Schwarz inequality. Okay, so several places basically we are using these two inequality. So just for the completeness I have also included this inequality, but you have to be sure that everywhere whenever inner product space, it means that vector space with inner product, and I can obviously define the norm by doing the square root of inner product, and then there exists two different inequality. And in previous class we have already seen that an inner product on a real vector v is the pairing that takes two vectors. Okay, and finally you can see that I map back to some kind of real vector. Okay, so somehow I am taking two elements from vector space v. V might be n dimension. Finally, you can see that on infinite dimension, finally I land up to some kind of real number. Okay, and I have told you that why people has done this kind of things, because whenever we are on real number, everything is ordered. Okay, so I can able to compare. I am able to compare this point A, B. Suppose that if I have written C and D, then there exists certain meaning that what is place value of C and D. Okay, and due to that reason, if you are in higher dimensional space and you are not able to compare something, then one way you try to map it to some kind of real space, because in real space I can able to compare. I can tell that something is bigger, something is smaller. But in higher dimensional space, I can just able to talk about the equality. I can able to tell that okay, whenever these two vectors are equal, then A equal to 1 and B equal to 2. Okay, I cannot able to tell that 1 2 or 2 or 1 which one is bigger and which one is smaller. That concept is not exist. Okay, in order to compare this, again I have to map it, okay, to one dimension. Means I can talk about length and 1 square plus 2 square and square root of that, 2 square plus 1 square and square root of that. Then we can tell that, okay, if I map to real number, then their length, whatever way I have defined, that is equal, like that. Okay, so these three properties are satisfied whenever we are talking about inner product space. In previous class we have already seen. Just for the sake of completeness of this lecture, I have again going to revise it. Okay, an inner product, whenever I have some kind of inner product, I have told you that you can just take the square root of that, then notion of norm comes into picture. Okay, and actually what happens, that why basically we have introduced these kind of notion, because whenever I have some kind of Euclidean space, then I know that what is length of this. Okay, but suppose you are in function space. Okay, why function space is so much important? Because whenever you are doing the mathematical modeling like this, or x dot equal to ftx, something like that, okay, you can see that solution of this is some kind of function. Okay, so somehow you are in some kind of a space that is generated the solution of this differential equation, that is function. Okay, so now you have to talk about the angle between two functions, distance of some functions, or distance between these two functions. Okay, and due to that reason I have to talk about some kind of a space, okay, where functions are involved. Okay, so I have to check three things. I have to check vector space, and we have already seen that whenever I have function, then and if I define the pointwise addition and pointwise scalar multiplication, then that will form the vector space. We have already seen. Okay, so I know that how to form the vector space. Now I have to define some kind of notion such that I can able to give guarantee that inner product comes into picture. Okay, and we know that if these three property will satisfy, then inner product, I can able to introduce the notion of inner product between any two vectors. Okay, so it means that in infinite many way I can able to define the inner product of two functions I have collected from some space. Okay, where I know that how to add two vectors and how to scale out some vector. Okay, and after that we have to check all property, and once I am able to do that, I can able to define the length also. In today's lecture I will tell you that how to define the angle between two functions. Okay, if we are in function space. Okay, so in previous class I have taken the continuous function in this bounded interval. I have told you that interval is nothing but the subset of the real number. So this is the real line, and I have defined the function only in this interval, and I have defined the inner product like this. Okay, and I have, if you see the previous lecture, those who has not attended, please go through that using this way it is possible to show that all three property, okay, property of bilinearity, property of positivity, and property of symmetry, all three property are satisfied. Okay, I have done that kind of exercise. Okay, now if you see the L2 inner product and norm of a function, that is just generalization of the Euclidean space, that is finite dimensional space. Now this is infinite dimensional space, so that kind of things actually I have remarked. Okay, so when I have already told you that what mathematician has done, actually they know how to manipulate the real number. Okay, they stack the real number, and after that they know how to manipulate the stacking of real number by doing, suppose I have some kind of real number a like x1, y1, z1, something like that up to rn. That doesn't matter, x2, y2, and up to zn, something like that. Okay, so I can able to define a plus b if I will do x1 and x2. So just by knowing that how to add real number, I can able to add this column vector too. Once they understood that, and this is finite dimensional space, means finite number of entry, then they also able to generalize it for some kind of entry where infinite number of tuples are involved. Okay, so suppose I have function, So we know that whenever I have some kind of function, so function number of element on the basis that is infinity, okay, and it is not difficult to verify. What you can do, you can take one function fx and you can do the Taylor series expansion about some point. Okay, so you are able to see that some constant term is there, x square x. I am assuming some kind of continuously differentiable function. Okay, so in this way we are able to visualize that whenever I have some kind of function, so that is going to lie in finite dimensional space. So now using the generalization of the notion of angle and length by the notion of the inner product and norm, I can able to talk about the distance between two functions, okay, or at least distance of function from the reference point, or able to talk about the angle between two functions also. Okay, so let us first try to talk about Cauchy-Schwarz inequality, because I am pretty much important, pretty much interested to know that how to calculate the angle between two functions. Okay, so obviously I have told you that everywhere first we are talking about the Euclidean geometry, where where field element is real number. Okay, and suppose I have constructed two vectors, okay, with help of this field, and I have to talk about the dot product. So in this way we are calculating the dot product, where v and w are the length, you can interpret as a length, and theta as the angle. Okay, and I know that cos theta is less than equal to 1, and due to that reason, if I take the absolute value in this side and these two are already a magnitude, so this relation will always satisfy. Okay, so this is true for any Euclidean space. Okay, and this fact, this proof is basically, you can see here, that involve the idea of geometry. Okay, so what we are telling, if I have two vectors, this vector v and w, and this angle is theta, then I can able to define the dot product, and after that I can use this kind of relationship and I will come up with this inequality. Okay, so in order to validation of this inequality, I have to see the geometrical interpretation. Okay, but in today's lecture I am going to give the algebraic proof. So whenever we are going to give the algebraic proof, it means that even if I don't know the geometrical interpretation, still this inequality is valid. Okay, so what is our claim? So this theorem is claiming that every inner product, okay, so I have some kind of vector space, you can take two entry and map to real number, and if that will satisfy three property, okay, and then I can able to define the inner product. And now what we are telling, that you can take the absolute value of inner product. And why we are taking just absolute value, you can see that whenever we are applying the inner product, at that time we are mapping to real number. Okay, and in real number, how basically we are able to identify the distance? Just using absolute value. We all are already well aware that if this point is from B and this point is A, so distance between here is B minus A, and we are taking the absolute value, because distance is never negative, and due to that reason this operator is telling that even if you are in this side, I don't care about that, my distance is still minus A like this. Suppose that you are at Limdi Choraha, and if someone asks you that how far the electrical engineering department, still you can tell that okay, 500 meters. And if someone asks you that where is our guest house, again you are going to tell that okay, that is 125 meter or something like that. Okay, so always you are using the positive numbers only. Okay, and in order to denote that positive number, basically we are using the notion of absolute value, and due to that reason I have taken absolute value here. You are able to take the norm also, that doesn't harm the notion. Okay, now after that this inequality is valid, and equality here, this is not a strict inequality, you can see that equality is also there. So if these two vectors are parallel vector, then it is possible to show that equality hold. Okay, let us try to see the general proof for that. So in order to prove that, I have told you that this is algebraic proof. So I have used some notion of vector space and notion of the inner product. whatever axioms we have of inner product I am going to use. Okay, so if w equal to 0, one of the vector equal to 0, then this inequality is trivial. Okay, so I am going to concentrate when w not equal to 0. Okay, so for that what I am going to do, I am going to take some kind of real number. Okay, and I have two vectors v and w, and whenever I have two vectors, so I can define these two vector addition because we are in vector space, and I can also able to define the scalar multiplication of one vector with that, and after that I have third vector, so I can able to add this vector with that, and again that is going to lie in vector space. Okay, and what I have done, I have seen that vector and I am going to take the square of this. Okay, so if you take the square of this vector, then that is always greater than 0. Due to that reason I have written like this. And if we have already seen that whenever we are talking about inner product, and if I replace v w by v, at that time v by v that is equal to the norm of this. In this way norm and inner product is connected, and same kind of property actually I have used here. And after that, using all three axioms, I am going to open it. If you open it, then it is not difficult to verify that this kind of notion comes into picture. Okay, and here you can see that if I substitute v equal to minus tw, then this equal to 0 and equality is going to hold. Okay, so that kind of things I have written here. Now what we are going to do, I am going to consider this, and I am assuming that since I have selected v and w from this vector space w, so I can assume that these two are fixed. Okay, and after that just I am changing the t. In this way also I can able to move in the space because t is any real number. Okay, so due to that reason, now I have to just worry about the equation with respect to t. And if you see the equation with respect to t, since a and v and w, you can take any v and w. Okay, and after fixing it, okay, and then you can select t. Okay, so then in this way I can able to move the whole space, and I am defining a as a w square, b as a this, and c as a this. Okay, and this should be greater than 0. Okay, so now you try to see that one thing, that what I have to make sure that this equal to 0, greater than 0. Okay, so this quantity at square 2bt plus c, that is always greater than 0. Okay, so I can tell that if minimum value of this that is greater than 0, so obviously maximum value is also greater than 0. Okay, and due to that reason I am going to find the minimum of this. Okay, and since this whole quadratic function is in t, and we know that in order to existence of the minima, rate of change should be 0 with respect to t, and due to that reason I have taken the differential of this, and in this way I can tell that I have this kind of point, and where now in order to check that there exists a minima, obviously I have to take the higher derivative p double dot t, and obviously it is possible to show that that is already minima for p double dash that is greater than 0, because I know that a is greater than 0 and c is greater than 0. Okay, so basically here 2a involved, and p double dot t means p d2 t by dt square, that is greater than 0. Okay, and in this way I can tell that this is the minima. Now substitute that point. Okay, so if that is true for minima, so obviously for all value that will, because we are talking about the, here it is possible to show that if you take another value, okay, so obviously this relation will satisfy, and from what I have done, I have just substituted value of t, and then I have established this kind of relationship. Okay, and now since I have to establish the Cauchy-Schwarz inequality, so what you can do, you can take the square root on the both hand side, and then you can take the absolute value, and obviously this kind of relation comes into picture. Okay, and when w equal to 0, then obviously this inequality will true. Okay, so in this way I have, you can see that here nowhere I have involved the geometrical notion. Just I have used the property of inner product, and we know that three axioms should satisfy that property I have used. Okay, and after that I have used the notion relation between inner product and norm, and then we have come up with this inequality. And due to that reason I am claiming that whatever this inequality, okay, any inner product space now you can take, okay, it might possible element of that inner product space, because whenever we are talking about inner product space I have vector space with inner product, and after that we have notion of norm. Okay, so vector space may be built with respect to column vector, with help of the matrices, with help of some kind of functions. Still I can able to define everything. Okay, now since we know that this inequality will valid in each and every norm linear space, now I have already told you that inner product is nothing but the generalization of dot product. Okay, and with help of the dot product we are defining the angle. Okay, and due to that reason, now since this is just generalization, so with help of the inner product I can also able to talk about the angle. Okay, angle between any two general element in this vector space. Okay, so just in place of the, because if you see the dot product, so whenever we are calculating the dot product we are doing like this: magnitude of v, magnitude of w, and cos theta, and after that cos theta we are defining v dot product w and mod v and mod w. Okay, so now whenever you are in generalized space, okay, inner product space, at that time I have to replace this value v dot w by the inner product. Okay, and after that this is actually replaced by the norm. So same kind of things we have written here. Okay, so now you are able to define angle between any two vectors, any two general vectors. So you can see here that v vector I have taken like this, w I have taken like this is column vectors, and v dot product of w is 1. Okay, and after that now you are able to define the angle like this. Okay, now here you can see that whatever way I have defined the dot product, so I have already told you that I can define dot product in several ways. In the previous class I have taken examples also, several example, v1 w1, after that v1 and after that again, so 2 v1 you can write, and after that I have w1 w2 like that. Okay, so this is classical way to define, that is exactly equal to the dot product of two vectors. Okay, so in that way I can able to define angle, but you can see that if you change the definition of inner product, okay, then for same vector is angle is also going to change. Okay, so basically angle is fully decided what kind of inner product you are going to define inside your space. Okay, so you have a space, and in a space you are able to define inner product in infinite many way. Okay, so definition, based on the definition of inner product, angle between two vectors is going to change. Okay, so that is sensitive, and due to that reason I have written here thus the measurement of angle, and obviously the length, because you can see that length, how basically we are defining the length. In order to define the length we are taking the inner product and the square root of that, so in that way we are defining the length. Okay, so both are depends on the choice of underlining inner product. Okay, so based on the inner product I can able to talk about the angle. Okay, same vector has different angle, same vector may have different length too. Okay, now I have already told you that if you generalize the concept of Euclidean space, okay, to inner product space, then you are able to do now lot of things. Okay, so now suppose if I have two functions px x and qx is x square. Okay, so I have linear function, I have quadratic function, so I can able to talk about the angle between these two. Okay, and angle between these two, again I can use this kind of formula. Obviously you can also able to define the distance. Okay, so first you can define the L2 L2 norm, and in the previous class we have already seen. And whenever we are defining the L2 norm, then we have to understand that what is the limit, because based on the limit also that inner product is varying. Okay, so in this way you are able to generalize the notion, and due to that reason basically people are generalizing. Okay, so Euclidean space is very limited, but now our requirement is not limited to that, and due to that reason I have to search some new notion, some new language to capture the new operation, and due to that reason we have introduced the notion of inner product space. Okay, now you can see that another inequality, that is called triangular inequality, and I have already told you that that is nothing but the generalization of the relation between length of this triangle. So you can construct one triangle, and it is in any higher dimensional space you are able to now construct. Okay, and it is possible to show that this property will satisfy. Okay, now again this equality is hold when both vectors are parallel, and proof is actually just the consequence of the Cauchy-Schwarz inequality. So what you can do, v plus w square you can take, and in this way you are able to write the relation between the norm and the inner product. Okay, and after that just you can open it using all three axioms. You can, whatever required axioms you can use, and here you can use the Cauchy-Schwarz inequality. And now you know that Cauchy-Schwarz inequality is actually valid in any inner product space, so you can use it. I have used the same, and after that we are getting the required result. So W actually here we have two equalities and we have to give. Okay, and due to that reason I will get this kind of inequality. Okay, so this inequality is also valid on every inner product space. Okay, because Cauchy-Schwarz inequality is valid in inner product space. With help of that I have driven this, and due to that reason this is also valid on any inner product space. And just for the sake of the checking, what you can do, you can consider the function space where I have some kind of continuous function, and I have defined the L2 norm, and after that I am going to check that between 0 and 1 this inequality will satisfy or not. So I have taken these two vectors. Okay, and vectors here in form of functions because we are in function space. And now in order to define the norm, we know that whenever we are talking about the norm, then we are going to repeat the inner product of same vector. Then I can write like this. So same kind of things I have done here, and after that and I know that L2 norm, whenever we are defining the L2 norm, at that time I have to define A and B, fx, gx. Suppose fx and gx are two function in some function space I have taken from there, and after that I have defined this kind of integral, and I have checked all properties satisfied. Okay, and you can see here that triangular inequality is also satisfied. So in this way you are able to confirm that. Okay, now in order to talk about triangular inequality, there is no need to just limit ourselves to the Euclidean space. Okay, I can able to talk about the inequality in function space too, matrix space too. Okay, now let us talk about the generalization. So this is basically generalization of this. Now I equal to n. So it is possible. So here we haven't given the proof. Just we are telling that. Okay, so a proof is little bit involved, and any standard mathematics books this proof are available. Okay, so due to that reason, just you try to understand that how basically again you have to use the concept of norm, concept of inner product, and you are able to drive this. Okay, and similar if you have L2 space, means where functions are involved, again you are able to use this kind of inequality. Okay, and whenever you are solving any control problem, any problem related to machine learning, at that time these kind of inequalities are involved. Okay, so due to that reason I have covered this kind of inequality. Now you are able to understand that which space we have to talk. Okay, now let us come to the norm. Okay, so when I have started this class I have told you that basically if you fix the inner product, okay, I have inner product space, and I have selected some inner product. Okay, and once you select the inner product, okay, and if you replace the same element, then basically notion of norm comes into picture. We have already seen this. Okay, so what does it mean? That if I know the inner product of two vectors, at the same time I am also able to define the norm. Okay, so it looks like the norm is actually always associated with inner product. Okay, but that is not the story. Okay, so I have to actually generalize the notion of distance. It might possible I can not able to define the inner product, still I can able to define the norm. Okay, so that kind of, with that kind of aim, now I am going to discuss the next part of this lecture. Okay, and what we are telling, that every inner product give gives rise to a norm that can be used to measure the magnitude or length of the element of the underlying vector space. Okay, so what kind of feeling basically comes from here, that if I have some kind of vector space, in order to define the norm, first I have to make sure that inner product should comes into picture. Okay, suppose that all three axioms of inner product will not satisfy, then question is that is it possible to define the norm or not? So answer of this question is yes. Okay, so what we are telling, that however not every norm that is used in the analysis and application arise from the inner product, that may arise from the another root. Okay, so to define a general norm on a vector space, we will extract those properties that do not directly rely on the inner product. Okay, so what basically we are going to do, in order to define the norm, we are just going to take the notion of the distance in the real line. Okay, and we know that how basically notion of distance on real line comes into picture. So suppose I have 2 points, and first behavior of the distance is that distance is always positive. Okay, so what I have to do, I have to define some kind of function block such that I can pass any quantity to this function block. Okay, such that I will always get some kind of positive number. Okay, so first axiom is basically telling that positivity. So you can take any vector v, and I have defined this kind of function. Okay, and this function, you can see that I am talking about greater than less than. So due to that reason I am talking about real valued function. So whatever this function, that is nothing but some kind of real valued function. Okay, so I have taken the element from vector space, I have defined some real valued function, and whenever that vector is passed through that real valued function, then that will give some kind of real number. That might be positive and negative, but here since we are just going to concentrate on the positive real number, because we are talking the generalization of length, and due to that reason I am assuming that whatever output of this particular functional block comes into picture, that should be greater than 0. Okay, and this equal to 0 if we are at 0, it means that if I am at reference point, then distance equal to 0. Okay, and second property is homogeneity. If you scale c by v, then this kind of scaling comes into picture. Okay, and after that third axiom is the triangular inequality. Okay, and we have just seen now that triangular inequality is satisfying an inner product space. So and inside inner product space, one can define the norm. So and these property they have extracted from there, but they are telling that these are the independent, that is not going to depend on the inner product selection. Okay, so even if I don't know how to define inner product, but still I can define the notion of norm, because I know that if I have to travel from here to here, and I have to travel here to here, then I can able to establish some kind of relation, like what is distance from here to here and what is distance from here to here, just by triangular inequality. So based on these three things, notion of norm comes into picture. Okay, so notion of, you can see that I have notion of inner product. With help of inner product, obviously I can define the norm, but here now I have generated the independent notion. Okay, and that v, norm v of some vector, that may not actually derive from the inner product. Okay, so let us again see the definition. A norm on a vector space V, assign a non-negative real vector V to each vector V. Okay, so it means that R plus comes into picture, and that should be satisfy these three axioms: positivity, homogeneity, and triangular inequality. Okay, if you see the inner product should satisfy bilinearity. Okay, but here just homogeneity is okay. Symmetry, here there is no need of symmetry, and after that if you check that, then that is positivity. So positivity is maintained. Okay, and here all other things are replaced like homogeneity and triangular inequality. Okay, so now let us come to the idea why basically notion of norm comes into picture. Okay, so general idea is like this: whenever we have deal with the vector space, you might have seen that I have talked about the four different subspace that is related with this vector space. Okay, four fundamental subspaces, and with help of that fundamental subspace I know that how to solve the linear algebraic equation. Okay, and at the same time I am able to define the notion of linear dependence. We are also able to see the notion of dimension. We are able to see the notion of the basis. These kind of notion we have already seen when I have deal with the vector space. Okay, so concept of linear operator so far I haven't discussed, but I will discuss it after some time. Okay, not in today's class but in another class. And we have already seen that linear dependence, so that kind of notion is actually comes from the vector space, and I can able to talk about the existence and uniqueness of the solution of algebraic equation. Okay, this kind of equation, when solution exists, when solution doesn't exist, in form of the column space, row space, we have already seen. So what is major limitation? Limitation is that there is no notion of distance or proximity. Means there is no notion of the distance or proximity. Means I cannot able to talk about the nearness in a space, time, or relationship. Okay, so what happens? What we have seen that whenever we are modeling some system using differential equation, and at that time if I am expressing differential equation with help of the first order differential equation, higher order differential equation by first order, that is a state space representation. So I have n dimensional quantity. Okay, so somehow what kind of things we require? If I have some kind of system, then I have to give guarantee that if I apply bounded input, then I know that whatever output that should be bounded. Okay, suppose if this system is stable, then in that way we are talking about the stability of at least the linear system, that if something give us bounded input, then I can tell that okay, if system is stable, then that will give us the bounded output. So how to tell that something is bounded? Okay, so for that I need some kind of notion of distance. Okay, that okay, in this way I can tell that in this vector and their boundary is going to lie here. Okay, so some distance kind of notion is still required, some ball kind of notion is still required, that is missing in the vector space. Okay, and due to that reason I cannot able to talk about the notion of convergence even if I do not know how to define the continuity. Okay, so these kind of notion, and continuity is very much important. I will tell you that based on the notion of continuity I can do lot of things. Okay, so that kind of things is not available with the help of this notion, and due to that reason what mathematician has done, they have taken the linear vector space and they have introduced the measure of length. Okay, so now measure of length can be defined in two different ways. Okay, so one route that directly you can define the measure of length with help of norm. Okay, second way what you can do, you can define the inner product, and after that since norm is associated with every inner product, then you can define the notion of length. Okay, and here I have already told you that I can able to define the norm, and it might possible that inner product may or may not exist. Okay, and due to that reason I have some special name basically comes into picture, that is called norm linear space. Okay, so So I hope that you are able to understand the notion difference between the inner product space and non-linear space. Okay, so inner product space basically contain the vector space together with the inner product, and after that I have also the notion of norm. Okay, because every inner product correspond to some kind of norm. Okay, but here now whenever we are talking about the non-linear space, then I have just a vector space and together with the notion of norm. That is just the difference. Okay, so there is no need to verify that inner product axioms are satisfied or not. Okay, now this space is called non-linear space, and this space is very important. Okay, most of result of linear system theory, whenever we are talking about system, either LTI system, LTV system, or some kind of system that is comes into picture after the linearization. Okay, even if I am talking about autonomous system and non-autonomous system, most of time we are talking about this space only. Okay, so how to define non-linear space? So that is nothing but some kind of ordered pair. So first pair is nothing but coming from vector space, and second pair is some kind of function. Okay, and this function is real valued function. Okay, and what is property of this function? That if you put any element here of this x, then they will map to the real number. Okay, and I have already told you that that is nothing but positive real number that comes into picture, because I have notion like distance. Okay, so all property of norm that should be satisfied. Okay, so what I have done, I have taken the all axioms of norm and I have taken all axioms of vector space and just I have combined both of them, and in this way we have given the name that as a non-linear space. Okay, and frequently we are using the non-linear space. You can see here that suppose I have some kind of column vector. Okay, from the beginning of the vector space I am talking about some kind of column space, function space, matrix space. Okay, so now what I have to do, I have to take each and every space at one time, and we have to see that how basically notion of norm is defined and how basically notion of non-linear space comes into picture. Okay, so first what I have done, I have taken the column vectors. Okay, and here I have actually constructed vector space just by the entry wise addition. Okay, and scalar multiplication in the classical way. Okay, now I have some kind of vector space. In that vector space, now I am going to define some kind of function such that all three axioms will satisfy. Okay, so it is possible to show that I can able to do this thing in infinite many ways. So let us try to understand in simple language. You might have seen that whenever we are talking about distance, I can able to represent distance using millimeter, centimeter, decimeter in different form. Okay, so suppose if you are going to buy some cloth, then you are not going to buy cloth in the kilometer, and due to that reason I need some kind of another measurement like meter. Okay, suppose you are going to build some kind of road, then at that time we are not using the notion of centimeter, we are talking in terms of the kilometers or something like that. Due to that reason different notion of the distance are required to characterize the element, and due to that reason similar kind of a story is here. I have a space, column space. For different application I need different notion of distance. Okay, obviously you have to make sure that all axioms, all rules should satisfy. Okay, and rule basically bound us such that I cannot go beyond some particular play, and due to that reason we have to make sure that all axioms should satisfy. Okay, so you can see that, and most of you already uses this kind of norm whenever you are doing any kind of analysis. So in today's lecture you are able to understand that why basically different notion of norm comes into picture. Okay, and their interpretation are also different. If you see geometrically, if you are going to plot, I will do that kind of plotting in next class. Okay, then you are able to see that if you are changing the norm, their interpretation will also change. Okay, and at least in finite dimensional space I can tell that all norm are equivalent. Okay, we will see that kind of point in next class. Today we are trying to understand the construction of norm. Okay, one more thing that is comes into picture here. I have already told you that whenever mathematician has developed some kind of notion, so if they know how to deal with real number, then they are not going beyond the real number. Okay, so whenever they are now proposing any new operation, they map that operation again to real number. Okay, so in real line they know how to define the distance between 2 points using absolute value. Okay, so they have developed some kind of hardware circuit how to calculate the absolute value. Okay, now whenever they have to develop any notion, everywhere they are just going to involve the absolute value. Okay, they are not going beyond that absolute value. Okay, and you can see that similar kind of things here. In order to define the infinity norm, okay, so infinity norm they have defined like max. Okay, so I have entry from x1 to xn. Okay, you can see each and every entry, and after that whatever maximum value you can pick up. Okay, that is the norm, that is called infinity norm. Okay, and in literature that is written by a small l infinity. Okay, all property it is possible to show that that is always positive, because I have even if positive and negative, I have first calculated the absolute value and then I am talking about the maximum of that. Okay, so and in hardware level just I have to to calculate the absolute value only. Okay, there is no need to develop separate operator. Okay, and after that or separate hardware, but still I can able to define this norm. Okay, and here you can see that all other exams, please just check it, that is very simple, means positivity, after that homogeneity and triangular inequality all will satisfy. Okay, now here you can see that this is called L1 norm. So L1, meaning of L1 norm, you can take absolute value of each and after that you can do sum. Okay, again you can see that in order to define that, they are just use at hardware level the absolute value, and after that they have done this summation. So this is called L1 norm, and similarly they can generalize to LP norm. Okay, so LP norm again absolute value is involved, just you can take the power of p and 1 by p. P can be anything from 1 to infinity. Okay, so now you are able to also define the L2 norm, and L2 norm is defined just like I equal to 1 to n and xi p, and after that 1 by p. And everywhere whenever we are talking about distance, during our school time we are using this kind of normally x square y square plus z square. Okay, so this is the story of norm whenever we are talking about vector space, where vectors are expressed in form of the column. All exams are satisfied. I haven't checked all exams. Okay, because in any mathematics book these exams or proof are available. Just I am telling you that how basically they are constructed. Okay, so you have to understand that how basically using a small hardware I can able to do lot of things. Okay, now let us come to the another space that is called the function space. Okay, I am assuming that I have some kind of continuous function on interval a and b. Okay, and in that interval now I know that whenever I have function, if I do the pointwise addition and pointwise scalar multiplication, then I can define the non-linear space. Again you can see that whenever I have just a column vectors, so entry is here finite. Okay, but in case of function entry might be infinite, and due to that reason addition is just converted into the integral. Okay, so integral addition operator, simple addition operator everywhere, now that is converted into integral operator. Okay, so in that space I can define, and here you can see that here I am going to use big L. Okay, so whenever my element is going to lie on function space, at that time I am going to use this kind of symbol L. Okay, whenever I have column vector and at that time we have to talk about norm, then we are going to use in that way. Okay, now you can see here that what basically we are going to do. Again I can use the absolute value of this. Okay, and I am going to integrate from a to b. Similar kind of things we can able to define for p norm, and obviously from here you can able to define the L2 norm too, that this is nothing but fx and square of this. Okay, from an integral a to b. In this way you are also able to define the L2 norm. Okay, so now you can see that if you have some kind of polynomial, so this is function, polynomial is defined like this in this interval, then you are able to define the distance of the polynomial, okay, using the help of norm. So I have calculated the different norm here, and you can see that selection of the norm, the distance is different for the polynomial. Okay, so now if you have just a column vector, then only note you are able to define the distance. Even if you have function, you are able to talk about the notion of distance with the help of norm. Okay, and due to that reason, that notion of norm is very much important. Okay, so now it is time to conclude the today's lecture. In today's lecture, what we have done, I have started with the inner product space. After that, I have talked about two different inequality which is valid in any inner product space, and then what I have done, I have maintained vector space, and with the property of distance I have introduced the notion of norm. Okay, so that notion of norm may or may not be driven from the inner product. Okay, and using with the help of that norm, I have talked about that if I have column vectors, okay, and that will satisfy the property of vector space, then how to define the notion of distance. After that I come to the function space, and again I have talked about the notion of distance. Okay, so with help of this notion of norm and underlining vector space, I can able to talk about the distance. Okay, once now we understood the length or distance, you can tell absolute distance, then we are also able to talk about the relative distance between two vectors. Okay, that is the story of the next class. So with this remark, now class is in from my side. If you have any specific question, then please let me know. Okay, so if you don't have any question, then class is over from my side. Thank you very much.